In this session, we are going to be looking at circle theorems and looking at the different types of circle theorems available. We're going to be working through each one bit by bit, and then hopefully by the end of the session, you'll be able to start using these in more complex exam style questions. We won't be applying these to exam questions in this session. Essentially, we are going to be learning the different types of circle theorems first. So what I would suggest you do before you get started on this section is to go back to the different types of the parts of a circle. So arc, sector, segment, chord, and all those types of areas of a circle, because it's really important that you understand those before you move on to these. So circle theorem 1. So a tangent to a circle makes a right angle with a radius at that point. So basically what they're saying is if you have a circle and you've got a radius and you've got a tangent, the angle between the radius and the tangent makes 90 degrees. So again, a radius, remember, it's from the center to the circumference, and a tangent skims past the circle at one point only. So that angle there is 90 degrees. Now, with a lot of these circle theorem questions, what you will find is you never really, or very rarely, are you asked to just look at one circle theorem. So they could implement or make you go through a question where you are using quite a few of these theorems in one go. So this might be the first step of the working out, but they do like to ask you for your reasons for each stage. So you do need to remember these. And my suggestion is potentially have a diagram on one side of a flashcard and have the actual reason on the other. And I've tried to make these reasons as easy as possible, because there are some sort of mathematic books and things like that overcomplicate the reasoning. You need a basic reason with your circle theorem. So this is the first one. The angle between the radius and a tangent is 90 degrees. If we look at circle theorem 2, so we've got a circle here, and these green lines are the radii, or each individual one's called the radius. And if you remember parts of a circle, the radius is basically always equal because it's coming from the center to the circumference, which is the same length throughout your circle. So if we look at this first triangle here that I've made, that's a chord, because we've got a line going from one part of the circumference to the other, and it's not running through the center. So we've got a chord and we've got our radii, and this makes an isosceles triangle. One of the properties of an isosceles triangle is that these two sides will be equal, therefore the base angles are equal. And sometimes you can get these questions that again require you to work as part of your answer on these types of questions. So you would need to realize that if this is 60 degrees, or let's make it 55, this would also be 55 degrees. Okay, likewise here we've got a slightly more spread out isosceles, but again you can see these two lengths are the same, therefore these two angles at the bottom, the base angles, are equal. So again, a triangle formed by two radii is isosceles. I have seen some students go into more complex reasoning, which is fine, which is to say that an isosceles is formed between two radii and a chord. That's fine. But again, try and make your reasoning as simple as possible so that you don't panic in an exam when you're having to reason. Okay, circle theorem 3. So if you have a triangle within a semicircle, it essentially makes a 90-degree angle. So you'll see here that the diameter, it is the hypotenuse of your triangle. And so if you can form a triangle there, then this angle here at the circumference is 90 degrees. Likewise, if we look this way, we've got a 90-degree angle up here. So I always see it as a triangle tucked into a semicircle. But just remember that the hypotenuse has to be the diameter. Okay, circle theorem 4. So this one's a slightly more different one. So we've got a chord here. So again, remember, a chord is a line that goes from one end of a circumference to the other. And bisecting. Now, bisecting basically means cutting in half. So bisecting a chord is splitting the chord exactly through the center. Okay, so this is your diameter here, and this is your chord. Okay, and the angle between your chord and your diameter is 90 degrees. And this line will always have to be the diameter for it to be cutting it exactly through the center, okay? Because halfway between the chord will be lying on that diameter. So an easier way to say that is a diameter bisects a chord at 90 degrees or at right angles. So this side would also be 90 degrees here. Those two arc lines here, these little marks, they're just showing that these two sides are equal in length because you've cut it in half. Okay, circle theorem 5. So a lot of my students look at this as a rocket style shape, which is fine because it does on the whole tend to, remind them of the circle theorem. But just please bear in mind that not all of these types of questions for circle theorem 5 end up looking like a rocket. And if I could drag this top corner and I move it, rotate it around the circumference and make it lower and lower, it's still this circle theorem. It just doesn't look like a rocket anymore. So just be very careful. But on the whole, this rocket does help students when it looks like this sort of shape. And again, I've seen this in combination with a different circle theorem. I think it might be circle theorem 7. And that's where you really do need to remember this theorem. And this theorem basically states that the angle at the center is double the angle at the circumference. So if A was 60 degrees, the angle at the center would be 120. Likewise, if this was 80 degrees here, then the angle at A would be half of that, which is 40. So you are technically looking for some form of a rocket shape. Just be aware that sometimes that angle up here can be quite lower down here. So the oval shape's a bit more squashed and less rocket-like. Circle theorem 6. So again, another way that my students have seen this is as butterfly wings. If you can see, these two triangles sort of form a butterfly. So the angles in the same segments, these top two, are the same as these bottom two, okay? So angles in the same segment are essentially equal. So if B is 40 degrees here, it's going to be 40 degrees up here as well. But they have to be in the same segment. Circle theorem 7. So here we have a four-sided shape completely encased within the circle. All four corners are touching that circle. And so what's really important is understanding that this is a cyclic quadrilateral. It's a four-sided shape within a circle, and the opposite angles in a cyclic quadrilateral add up to 180. So A plus C together makes 180, and D plus B together makes 180. So if A was 100 degrees, C would be 80 degrees, and so on. Again, I've seen a rocket shape within this one. So you might have another sort of two lines here going in like that. So you've got a rocket on the top. So we would then say that those opposite angles are adding up to 180. Circle theorem 8, so there's two more. So circle theorem 8 is two tangents that are coming from a single point that touch your circle. Those two tangents are basically equal. And again, I've seen a question that combines the angle between a tangent and a center. That makes 90 degrees. So I've seen that combination as well. And sometimes you can be asked to find this top angle. Sometimes you can be asked to find this center angle. So these two tangents are the same length. And then the final circle theorem is the angle between a tangent and a chord, this is the more complex one, is equal to the angle subtended from the ends of the chord in the alternate segment. In other words, if you have a tangent and then you have a triangle within your circle, the angle between the left-hand side, between the tangent and the side of the triangle or the chord, is equal to the interior opposite angle in the triangle. So B is equal to the interior opposite angle, so it would be this one. So always work with the opposites. And that's the most complex circle theorem that you need to memorize. And that's all of them.